The third stage in simulation methodology is what we call as the implementation stage. So in this particular stage, we try to discuss the implementation of algorithm in GNumeric and Scilab for the particle and 1D box. So implementation stage has 3 steps again. First step is to write the algorithm, that is the stepwise procedure, let us say in simple language, so that we understand what are the various things to be achieved. And then second thing is to implement it in GNumeric kind of worksheets actually, which will sort of make the algorithm come alive. And once we are clear about each and every step and what it is producing in the algorithm, we can go and implement the code in Scilab or Python, depending upon whatever we are familiar with. And finally, of course, we have to test it on a known problem and ensure that the algorithm parameters are optimized so that the code is ready and gives us the correct results. So the step 1 is write the algorithm. So in the algorithm, we have the initialization step, and so this consists of, now our modeling methodology helps us a lot, because there you see we have clearly identified what are the object variables, interaction variables. So we have to first initialize them. So in this case, of course, ME, that is mass of the electron, is equal to 1. And interaction variables, V0, we can choose it to be a very large number. It's basically infinity, but we will choose it as a very large number. And then the range of interaction is limited to the width of the box, which is A, which we are taking as 1 unit. That is, in this case, we should say, because we are using atomic units, V0 is 10 power 6 Hartree and A equal to 1 Bohr. And now initialize the algorithm parameters. The algorithm parameter in this case is, because we are using central divided difference techniques, so the only algorithm parameter available for us is the step size H. So that would determine the matrix size in turn. Okay, so H equal to 0.1. And so that is the, so we are having the box from 0 to 1. So step size of 0.1 means we will have 0, 0.1, 0.2, etc. up to 1. So if you leave out 0 and 1, that means 0.1 to 0.9. That means we will have a 9 by 9 matrix automatically coming up. So the step size will automatically determine the matrix size for us. And then, of course, we need to initialize any constants that are required in our code. Okay. So in this case, for example, we have the factor f to be equal to minus 1 by 2 h squared, where h is the step size. Okay, so this is the first step, that is initialize the various object interaction variables, algorithm parameters, and any other constants required. The second step is we define the potential. So here what we do is we initialize an array x from 0 to a in steps of h. So that the way I have already told you. And then we generate the potential as an array v at each of these x values. So here I am putting a small v so that we can use a capital V for the matrix later. Okay, so these are just some symbols basically naming the various variables that we have. That is up to us how we want to choose them. And then finally, of course, it will help us to plot the potential and see whether we are getting the right form for the potential or not. The next step is to generate the Hamiltonian matrix. So this has again 3 parts to it. First, create the potential matrix V, where we put all the Vj's along the diagonal. And then create the A matrix, which is a tridiagonal matrix, which represents the operator for second derivative. That is minus 2, 1, 0, 0, then 1, minus 2, 1, like that, right? That we have seen. And then finally, we can generate the Hamiltonian matrix as F star A plus V. So once we get this H matrix, the last step is to determine the energy eigenvalues and eigenvectors. And so that can be done in GNumeric using the eigen command, and in Scilab using the spec command. Similarly, in Python, I think it's the eig command. So this will generate the eigenvalues and eigenvectors for the H matrix. So once we obtain the eigenvalues, we can check the obtained eigenvalues, how accurate are they with respect to the analytical eigenvalues. That is En equal to n squared pi squared h cross squared 2 ma squared, where h cross squared you have to put 1 and me equal to 1. Okay, so if they both are very close, then our step size is good. Otherwise, what we have to do is we have to reduce the step size to get better match between the numerical and analytical results. Then finally, of course, we can plot the eigenfunctions and see whether they are looking the way they are supposed to, because we know the sign functions. And once we are through with this, then we can finally determine the probability densities and expected values, and again cross check them with what is expected. So this is the algorithm. Now let us look at how to implement it next.